Okay, frequency response. This is section 2, page 9, part 1 of section 2, and it's about frequency response. And frequency response is one of the most commonly used terms in audio, but if you don't know what that means, it's okay, because here in section 2, we're going to define it and examine it and apply it and describe it. And let's start with the definition, though. So any audio device, doesn't matter if it's microphones or headphones or a speaker, any audio device has a frequency response, meaning that the device responds to frequencies meaning that how a device responds to the frequencies passing through it, or the effect an audio device has on the frequency balance, is called a frequency response. I'm going to read from the book really quick. The frequency response of a device describes the relationship between the device's input and output with regard to signal frequency and amplitude. Another term for this is magnitude response. In its common usage, the frequency response describes the usable range of signal frequencies which the device will pass through from input to output. Okay, so remember when I was talking about equalizers? In understandable terms, basically a frequency response is like the device's hardwired EQ. So that's what they mean when they say the relationship between the device's input and output with regard to signal frequency and amplitude. When they say device's input and output, it means energy goes into a device and energy comes out of a device. The frequency response is basically the difference between the energy that's being put into a device and the energy that's emitted or produced by the output. So imagine with me a scenario. An unknown signal processing element, let's call it a black box, okay? This black box is connected to a sine wave generator and a level indicator. So the level indicator is the output, the black box is the signal processor, and the black box is being fed sine waves from a sine wave generator, all right? Again, this black box is not a specified brand or a specific piece of equipment. It's just serving as a representation for any random signal processor, all right? So say this sine wave generator, this oscillator, is consistently producing the same output level at all frequencies. So the input level to the black box is constant. In other words, the oscillator is producing the same output level across the tonal spectrum, across the audio range from the lowest frequencies to the highest frequencies. And the black box is receiving that same constant input at all frequencies. The frequency response is what we see occur to the output level of the black box, right? So the sine wave generator, again, is producing the same level output regardless of the frequency, and the black box is receiving the same level input regardless of the frequency. But let's say the output of the black box is not constant. In other words, it's not producing the same level output across the audio range. The frequency response shows us the range of frequencies that the black box will pass from input to output, and what fluctuations in output level, if any, occur within that range. So this output, this level indicator, let's say there's no change in the output level, assuming that there was a constant input level to the device under test. That would mean there would be a perfect or flat frequency response. In other words, as we sweep the oscillator through the audio range, this level indicator does not budge, doesn't move at all. I love how the book defines frequency response. Frequency response gives us an indication of the fidelity or accuracy with which the device transfers a signal from input to output. The less deviation there is in output level across the stated frequency band, the more faithfully the signal at the output will reflect the signal at the input. And that's great. In its simplest terms, frequency response is just how accurate the device is. How much is it fucking up the intended sound? So basically, let's say you put on one pair of headphones, right? And with this pair of headphones, you're saying, ooh, I love how crisp the high end is. And then you put on a different pair of headphones and you say, ooh, the bass sounds much better in these. You might prefer one pair of headphones over another, but what you're really saying is, ooh, this pair of headphones is fucking up the intended sound just right. But aren't you a little curious? What is this song really supposed to sound like? Have your ears really ever heard the song exactly how it was supposed to be heard? Frequency response, do 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 do. So basically, there are two things to remember. One, this is assuming the input to the device is constant, meaning that frequency response is kind of like useless if the device going in is not, at the same constant level, because you can only really measure it as long as you know that, the input is constant. But the second thing is there's a difference between frequency response and frequency range. So the term frequency response is used only to refer to signal processing devices and transducers. So signal processing devices and transducers, frequency response. But when you're referring to signal generating devices, this means musical instruments and oscillators and so on, that proper term to use is frequency range. So there's another thing that I didn't write down, but I want to remember. So magnitude response, I don't remember what that is. Another term for this is magnitude response. The frequency response of a device describes the relationship between the device's input and output with regard to the signal frequency and amplitude. Another term for this is magnitude response. In its most common usage, the frequency response describes the usable range of... Okay, so magnitude response is just another term for frequency response. Great. Let me write that down really quick. Sorry. Magnitude response is just another term for frequency response. The end. All right. In its simplest form, what's going on? In its simplest form, a typical frequency response specification might read frequency response, 30 hertz to 18 kilohertz, plus or minus 3 decibels. Okay, so let's break that down really quick. 30 hertz to 18 kilohertz is the range, and then it's accompanied by the qualifier plus or minus 3 decibels. This is called the tolerance of the specification. The tolerance tells us the maximum deviation in output level that we can expect over the stated range if the output level remains the same at all frequencies. So, without a stated tolerance, the frequency response specification is useless, like I said, since we're left to guess the unit's effect on the signal. So there might in fact be horrendous peaks or dips in the response, and these could alter the signal considerably. While a tolerance of plus or minus 3 decibels is often assumed if not specified, such an assumption is at your own risk. There is usually a reason why such an important qualifier is omitted from a specification. So, I need to figure out how to say this in idiot terms. I'm going to move on and then I'll explain it later. Some audio devices exhibit extraordinary flat frequency responses, as shown in figure 2-4. Such a response curve would be characteristic of a power amplifier or a line amplifier. So a flat frequency response basically means that there are not a lot of dips or anything like that. That's what that is. 2-4. And that's kind of what this looks like when it says 30 hertz to 18 kilohertz plus or minus 3 decibels. That's what it is. 30 hertz to 18 kilohertz plus or minus 3 decibels, which means it's not deviating from the average or the line, the reference level by more than 3, negative or positive 3 decibels. So in such cases, the frequency response limits are usually taken to these points where the unit's output level is 3 decibels below the average or the reference level. The frequency response specification for these devices plotted in figure 2-4 would read 20 hertz to 30 kilohertz, 0 and -3 decibels. So that is this one. Let me show you. Basically, see how it's very, very flat. That's reference level. That's 0. Right here, that's -3. So at 20, it's -3. At like 30,000, it's -3. But the other ones are 0. So in idiot terms, I guess what that means is between 20 hertz and 30 kilohertz, the frequency response level could be an average, or at the reference level, which is 0 decibels, or 3 decibels below average or the reference level. If the frequency response of a device in question greatly exceeds the total range of human hearing, which is 20 Hz to 20 kHz, the frequency response may be specified by simply stating the total response deviation within the audible range. The specification of the device whose response is shown in figure 2-5, which I'll show you in a second, might read 20 Hz to 20 kHz, 0, and then 0 decibels, and then -1 decibel. So check this out. Look how flat that is. It's from 20 to 20K. It's like 0. It's at reference level. But then at 10 and at 40K, it really dips off, and it's about -3 decibels. So alternatively, if one chooses the -3 decibel points as the frequency limits, the specification would read 10 hertz to 40 kHz, 0, -3 decibels. So basically, the difference is the frequency response for that first one that only had -1 was only from 20 hertz to 20 kilohertz, which is the total range of human hearing. But the one that went down to -3 was the same, the same reference, their same response plot, but it went down to a 10 hertz, which is 10 hertz below the human hearing range, and then it went up to 40 kHz, which was 10,000 hertz higher than the human hearing range, and that one had a frequency response that was -3. So basically, this graph that I'm showing you right now, right there, that is a flat frequency response plot of a device with one very wide bandwidth. Boom. Hope that's good. Frequency response measurements and specifications are sometimes made on an octave or 1/3 of an octave basis. Such measurements are far lower in resolution than those described above. Okay, so frequency response measurements or specifications that are made on an octave or 1/3 octave basis are far lower in resolution than those described above. Okay, got it. So how? What do you mean far lower in resolution? They are widely used with loudspeakers. Okay, so frequency response measurements or specifications that are made on an octave or a 1/3 octave basis are widely used with loudspeakers. Yes. Okay. Frequency response measurements or specifications that are made on an octave or a 1/3 octave basis are widely used with loudspeakers. Why? If frequency response measurements or specifications are made on an octave or 1/3 octave basis, and that are far lower in resolution than those described above, why would they be used on loudspeakers? Well, because they provide a good correlation with the characteristics of human hearing. Oh, okay. So the 1/3 octave and octave basis are they provide a good correlation with the characteristics of the human hearing, I guess. Okay. So but you didn't really answer my question. What makes the resolution far lower? Well, first, it's important to know that the octave is a special musical interval between two tones, formed when the ratio between the frequencies of the two tones is 2:1. The ear hears an equivalence between the tones when this is the case for the For this reason, the pitches in successive octaves in the musical scale are named with the same letter. So, okay, Poindexter, say it in English. So, is A at 440 hertz, and is A at 220 hertz. Those are octaves. The higher note was vibrating at 440 hertz or 440 cycles per second, meaning that its frequency is 440 hertz, but the lower note, or an octave down, was vibrating at 220 hertz or half as many cycles per second. So this is what they mean when they say the ratio between the frequencies is 2:1. Okay, so I guess now I understand the physics behind an octave, but I'm still confused about its relevancy and how frequency response measurements or specifications made this octave or 1/3 octave basis far lower in resolution. Well, with regard to frequency, the octave interval is much wider at high frequencies than at low frequencies. For example, one octave at 40 hertz, one octave above 40 hertz is 80 hertz. So a 40 cycle wide interval. So the octave between 40 hertz, so 40 hertz and then an octave up is 80 hertz, which is a 40 cycle wide interval. But an octave above 1000 hertz is 2000 hertz, which is 1,000 cycle wide interval. Yet we hear both of these intervals as musically similar, which is crazy. So basically what you're saying is that vibrations, meaning frequencies, function algebraically, or rather logarithmically. So higher frequencies, let me put logarithmically, rather logarithmically. I wrote this when I was still an idiot. Okay, so higher frequencies have a much larger in between octaves than lower frequencies. You know what I mean. Even though we hear the same intervallic difference, yeah. So let's put it back into Poindexter terms. This is because the ear's response to frequency is logarithmic in character, like I just said. So I'll explain logarithms in the next section. But this is why audio response plots, such as those shown in earlier in this section, employ a logarithmic scale to indicate frequency. So on this type of scale, the divisions pack closer and closer together as the frequency increases, up to a decade, 10, 100, 1000, logarithmically, of course. Then the spacing interval repeats. Octave and 1/3 octave measurements are designed to divide the linear audio frequency scale, which we do not perceive to be linear, into perceptually equal increments. Like intellectual gibberish. Okay. In frequency response measurements and specifications, then let me show you this. Look at this bar graph. That's a figure 2.6 frequency response measured in 1/3 octave band. So it's a bar graph, right? I hope you can see that. In frequency response measurements and specifications, then the average level in each incremental division is given, normally in bar graph form, as I just showed you. So even though we perceive the same intervallic difference regardless of frequency, the ear's response to frequency is logarithmic in character, meaning that the lower the frequency, the more spaced out, and as the frequency increases, the divisions are packed closer and closer together. Here, the center frequencies of the bands are spaced 1 octave. So here meaning the graph that I just showed you. The center frequencies of the bands are spaced 1/3 octave apart. The specific frequencies given on the horizontal axis are standard center frequencies for 1/3 octave measurements. These same centers are also used for filters and 1/3 octave graphic equalizers. The standard used is known as ISO, or International Standards Organization. So you know that if you have an equalizer with ISO standard octave, it's going to be 1/3 or octave spacing. So it'll coincide with the bands measured in ISO standard real-time analyzer. Blah, 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 blah. So idiot terms is frequency response measurements can be used in octave bands or in logarithm measurements. So basically, the graph you're seeing, instead of a sine wave, the excitation signal used for measurements, like this special sign called pink noise. Basically, pink noise is a randomly generated signal that excites all the audio frequencies with equal energy per octave. So it sounds much like a rushing waterfall in that this is pink noise. So each octave, each frequency is equally excited. And excitation signal, that's a phrase we don't know. Basically, pink noise can be used as an excitation signal, for instance. It would seem that excitation signal means the energy of the signal as reflected by the equalizer. So I'm going to keep reading. Since there are more frequencies packed into each upper octave than there are each lower octave, pink noise rolls off at higher frequencies. This means that there's less energy at any single high frequency than at any single low frequency, so that when all the noise is added up, it equals all the noise in any lower octave. Okay, so let me move on. When pink noise is used as the excitation signal, the output of the device under test is filtered in octave or 1/3 octave bands, of course, and the average energy in each band is measured separately. So, it is important to note that the measurements like this can conceal as much as they reveal. While they provide a good picture of the general characteristic of the device's frequency response, very narrow peaks or dips can be completely missed by this technique. In a reverberant space, the measurement may say more about the room than the loudspeaker under test. So, in idiot terms, it should be no surprise that the bar graph would be inaccurate. While they do provide a good picture in general of the characteristic of a device's frequency response, the specificities will be more concealed.